Good evening. Tonight, we'll travel through space without leaving this room. We'll visit worlds of ice and fire, rings of ancient dust, moons with hidden oceans, all of it orbiting our sun, that ordinary star in this corner of the Milky Way. Let your eyes close if they wish. Let your breathing find its rhythm. These aren't facts to memorize, but stories to drift through, like starlight filtering through evening clouds. We begin with distance, with darkness, with the vast quiet between worlds. The solar system is mostly empty space, a few small worlds scattered through an ocean of nothing. If you shrank the sun to the size of a basketball, Earth would be a peppercorn orbiting 26 meters away, and Neptune would circle over half a mile distant. Most of the volume contains only vacuum, darkness, the faint pressure of sunlight spreading outward. Our sun formed roughly 4.6 billion years ago, from a cloud of gas and dust floating in space. Something triggered this cloud's collapse, perhaps the shock wave from a nearby exploding star. Gravity drew material inward, the cloud spinning faster as it contracted, flattening into a disk with a dense hot core at the center. In that core, pressure and temperature climbed until hydrogen atoms began fusing into helium, releasing tremendous energy, and the sun ignited. The leftover disk of dust and gas around the young sun contained the raw materials for planets. Near the sun, where temperatures ran high, only metals and rocks could condense into solid form. Water and other volatile compounds remained gaseous, swept outward by solar wind. This is why the inner planets, Mercury, Venus, Earth, Mars, are small, dense, and rocky, while the outer planets grew massive from accumulated ice and gas. Tiny grains of dust in the protoplanetary disk stuck together through static electricity, forming pebbles. Pebbles collided and merged into boulders. Boulders accumulated into planetesimals, objects ranging from kilometers to hundreds of kilometers across. These planetesimals then collided, sometimes merging, sometimes shattering, gradually building larger bodies through violence and patient accumulation. The process was neither smooth nor quick, requiring tens of millions of years. Giant impacts between growing planets reshaped worlds repeatedly. Earth itself suffered a collision with a Mars-sized object early in its history, a catastrophic impact that vaporized rock and sent debris into orbit. That debris coalesced into our moon, born from violence, a companion ever since. Mercury, the closest planet to the sun, is a world of extremes. Temperatures on its sun-facing side reach 430 degrees Celsius, hot enough to melt lead, while the night side plunges to minus 180 degrees. With almost no atmosphere to distribute heat, day and night exist in separate thermal universes on this small world. The temperature difference between them exceeds 600 degrees, the greatest of any planet. This tiny world, only slightly larger than our moon, possesses a disproportionately large iron core. Scientists believe a massive impact early in Mercury's history stripped away much of its rocky mantle, leaving behind a world that's mostly metal. The surface, covered in impact craters, tells the story of 4 billion years of bombardment, a record preserved in the absence of atmosphere or geological activity to erase it. Mercury's orbit is peculiar, more elliptical than other planets. As it circles the sun, its distance varies from 46 million kilometers at closest approach to 70 million at its farthest point. This variation, combined with Mercury's slow rotation, creates strange effects. On parts of the surface, The sun appears to rise, reverse course, and set again, then rise once more, a double sunrise caused by the interplay of orbital and rotational speeds. The planet completes 3 rotations for every 2 orbits around the sun, a gravitational resonance that keeps the same face pointed sunward at alternate perihelion passages. This dance between rotation and revolution means a single day on Mercury, from sunrise to sunrise, lasts 176 Earth days, twice as long as Mercury's year. Time moves differently there, a reminder that these measures we use are local, arbitrary, tied to our own world's particular motions. Venus, Earth's near twin in size, could hardly be more different in character. Hidden beneath perpetual clouds, its surface bakes at 465 degrees Celsius, hotter even than Mercury despite being farther from the sun. The reason is atmosphere, a crushing envelope of carbon dioxide 90 times thicker than Earth's, creating a runaway greenhouse effect that trapped heat billions of years ago and never released it. The atmospheric pressure at Venus's surface equals that a kilometer beneath Earth's oceans, enough to crush most spacecraft within minutes. Soviet Venera probes that successfully landed there in the 1970s and 80s survived only briefly, transmitting a few images of a rocky plain beneath orange skies before succumbing to heat and pressure. Those images showed flat stones scattered across the ground, basalt from ancient volcanic eruptions, weathered smooth by the dense atmosphere. Venus rotates backward compared to most planets, spinning slowly in the opposite direction, taking 243 Earth days to complete one rotation. Its day is longer than its year, which lasts only 225 Earth days. Why Venus rotates retrograde remains uncertain. Perhaps a massive ancient impact knocked it askew, or perhaps gravitational interactions with the sun gradually reversed its spin over billions of years. The planet keeps this secret wrapped in its acid clouds. Those clouds aren't water, but sulfuric acid, products of volcanic eruptions that have covered Venus's surface with relatively young lava plains. The entire surface appears to be no more than 500 million years old, suggesting some global resurfacing event erased older terrain. Whether this involved catastrophic volcanism or gradual renewal through ongoing activity, scientists debate. Venus remains mysterious despite numerous probes, its surface hidden, its history ambiguous. Earth, our home, is the only world we know with certainty harbors life. From space, it appears blue and white, oceans dominating the visible surface, clouds swirling in patterns that reveal atmospheric circulation. This view, first seen by astronauts, showed us our planet's fragility, a thin layer of air, a sphere of water, the only known refuge for life in the observable universe. What makes Earth habitable involves numerous factors working in concert. Distance from the sun keeps temperatures moderate, water existing as liquid, ice, and vapor. A large moon stabilizes the axial tilt, preventing wild climate swings. Plate tectonics recycles carbon dioxide, regulating greenhouse effects over geological time. A magnetic field, generated by the liquid iron core, deflects solar wind that might strip away atmosphere. Each factor contributes to conditions that permit life. Water covers 71% of Earth's surface, a global ocean interrupted by continents. This water cycles continuously, evaporating from oceans, forming clouds, falling as rain or snow, flowing through rivers back to the sea. Life depends on this cycle, and life also influences it, plants affecting rainfall patterns, marine organisms producing clouds by releasing organic compounds that serve as condensation nuclei. The system is deeply interconnected, life and environment shaping each other. The atmosphere, that thin envelope extending about 100 kilometers above the surface before fading into space, contains the air we breathe, shields us from harmful radiation, and creates weather. Its composition, 78% nitrogen, 21% oxygen, traces of other gases, results partly from biological activity. The oxygen in particular derives almost entirely from photosynthesis, billions of years of life gradually transforming the atmosphere into something breathable. Earth's moon orbits at an average distance of 384,400 kilometers, close enough that we see it as the second brightest object in our sky. It formed from debris thrown into orbit by that ancient giant impact, and it has been slowly drifting away ever since, currently receding about 3.8 centimeters per year. Tidal forces between Earth and Moon cause this gradual separation, the same forces that create ocean tides that have gradually slowed Earth's rotation over geological time. The Moon's gravitational pull creates two tidal bulges in Earth's oceans, one facing the Moon, one on the opposite side. As Earth rotates beneath these bulges, coastlines experience high and low tides. This constant flexing dissipates energy, slowing Earth's rotation by about 2 milliseconds per century. 4 billion years ago, days were only 5 hours long, the Moon much closer, its apparent size in the sky enormous compared to the present. Time stretched slowly as tides work their patient influence. Mars, the red planet, has captivated human imagination for centuries. Its color comes from iron oxide, rust, that covers much of the surface, the remnant of ancient water that oxidized iron in rocks. Once, Mars had liquid water on its surface, rivers carved channels visible today, minerals formed in standing water deposited in lake beds. But Mars lost most of its atmosphere billions of years ago, and the water disappeared, frozen in polar ice or absorbed into the ground. The planet is smaller than Earth, with only about a third the gravity. Its thin atmosphere, mostly carbon dioxide, provides almost no pressure, less than 1% of Earth's. Water cannot remain liquid at the surface under these conditions. It either freezes or evaporates directly into vapor. Yet evidence of ancient rivers, lake beds, and deltas suggests a warmer, wetter past, a Mars that might have been habitable, might even have hosted life in its early history. Olympus Mons, the largest volcano in the solar system, rises from the Martian surface to a height of 21 kilometers, nearly 3 times taller than Mount Everest. Its base sprawls 600 kilometers across, a mountain so massive it would cover most of France. The summit caldera, the collapsed crater at the peak, is 80 kilometers wide and several kilometers deep, evidence of enormous volcanic eruptions that occurred millions of years ago, when Mars was still geologically active. Valles Marineris, a system of canyons stretching 4,000 kilometers along the Martian equator, dwarfs Earth's Grand Canyon. In places, these canyons plunge 7 kilometers deep and spread 200 kilometers wide. They likely formed through a combination of tectonic cracking as the planet cooled and subsequent erosion, possibly including water flow in Mars's wetter past. Standing on the edge, you could not see the opposite rim. It lies beyond the horizon of this small world. Mars has 2 small moons, Phobos and Deimos, both probably captured asteroids rather than bodies that formed alongside Mars. Phobos, the larger, orbits so close to Mars that tidal forces are slowly pulling it inward. In about 50 million years, it will either crash into Mars or break apart from tidal stress, forming a ring around the planet. These moons are irregular chunks of rock, potato-shaped. Their surface is covered in craters from eons of impacts. Between Mars and Jupiter lies the asteroid belt, a region containing millions of rocky bodies ranging from dust grains to Ceres, a dwarf planet nearly 1,000 kilometers in diameter. These are remnants from the solar system's formation, material that never coalesced into a planet, prevented from doing so by Jupiter's gravitational influence. The total mass of all asteroids combined equals less than 4% of the Moon's mass, most of the region actually empty space. Ceres, the largest object in the asteroid belt, contains about a third of the belt's total mass. It's massive enough that gravity has pulled it into a spherical shape, though not large enough to clear its orbital neighborhood of other bodies, which is why astronomers classify it as a dwarf planet rather than a full planet. Beneath Ceres's rocky surface lies a layer of ice, possibly even a subsurface ocean, water preserved from the solar system's formation. Jupiter, the giant of planets, contains more mass than all other planets combined. Its volume could hold 1,300 Earths, yet it has no solid surface, being composed almost entirely of hydrogen and helium, like a star that never quite gained enough mass to ignite fusion. What we see as its surface is actually the top of cloud layers, bands of ammonia ice crystals flowing in opposite directions, creating the characteristic striped appearance. The Great Red Spot, a storm larger than Earth, has been raging for at least 350 years, possibly much longer. It's an anticyclonic storm, rotating counterclockwise, with wind speeds exceeding 400 kilometers per hour at its edges. The storm's red color comes from complex organic molecules created by solar ultraviolet light interacting with ammonia, methane, and other compounds in Jupiter's atmosphere. This storm is slowly shrinking, observations over the past century showing it was once much larger, and whether it will eventually dissipate remains unknown. Jupiter's immense gravitational field affects the entire solar system. It has captured numerous moons, at least 79, confirmed as of recent counts, and acts as a cosmic vacuum cleaner, its gravity attracting comets and asteroids that might otherwise impact the inner planets. Some scientists believe Jupiter's presence made Earth more habitable by reducing the bombardment rate, though others argue Jupiter also sends objects inward through gravitational perturbations. The giant planet's influence is complex, its effects both protective and dangerous. The four largest Jovian moons, discovered by Galileo in 1610, are worlds unto themselves. Io, the innermost, is the most volcanically active body in the solar system, its surface constantly being resurfaced by sulfurous eruptions. Tidal heating causes this activity. Jupiter's gravity squeezes and stretches Io as it orbits, generating internal heat through friction. The moon's volcanoes spew plumes of sulfur dioxide hundreds of kilometers high, creating a thin atmosphere and painting the surface in yellows, oranges, and reds. Europa, slightly smaller than our moon, holds an ocean beneath its icy surface. The surface ice, smooth and crisscrossed with fractures, conceals a global ocean perhaps 100 kilometers deep, containing more water than all of Earth's oceans combined. Tidal heating from Jupiter keeps this ocean liquid despite the moon's distance from the sun. Where there's liquid water and heat, there might be life. Europa represents one of the most promising places to search for extraterrestrial organisms in our solar system. Ganymede, the largest moon in the solar system, exceeds even Mercury in size. It's the only moon known to generate its own magnetic field, suggesting a liquid iron core. Like Europa, Ganymede likely harbors a subsurface ocean, this one sandwiched between layers of ice at different pressures. The surface shows two distinct terrains: dark, heavily cratered regions billions of years old, and lighter, grooved terrain that's been tectonically resurfaced more recently. Callisto, the outermost of the four Galilean moons, appears the most heavily cratered object in the solar system, its ancient surface showing little sign of geological activity. Yet beneath that dead exterior, evidence suggests another subsurface ocean maintained by radioactive decay and residual heat from the moon's formation. Callisto orbits beyond Jupiter's most intense radiation belts, making it a potentially safer target for future human exploration than the other Galilean moons. Saturn, the jewel of the solar system, famous for its spectacular ring system, is the least dense of all planets. It's composed mostly of hydrogen and helium, and if you could find an ocean large enough, Saturn would float. Its average density is less than water. Like Jupiter, it's a gas giant, though smaller and less massive, with wind speeds that exceed those on Jupiter, reaching 1,800 kilometers per hour near the equator. The rings, while visually striking, are surprisingly thin. They extend hundreds of thousands of kilometers across, but are generally less than 10 meters thick, like a sheet of paper scaled to the size of a football field. They consist of countless particles ranging from dust grains to house-sized chunks, mostly water ice, orbiting Saturn in a flat plane. Gaps in the rings, like the Cassini division, result from gravitational resonances with Saturn's moons, which sweep regions clean of particles. These rings may be temporary on geological timescales. Some scientists suggest they formed relatively recently, perhaps only 100 million years ago, when a moon ventured too close to Saturn and was torn apart by tidal forces. Others believe the rings are primordial, remnants from Saturn's formation. Recent data from the Cassini spacecraft suggests the rings are slowly raining down onto Saturn, material spiraling inward, and they might disappear entirely in another 100 million years. Saturn has at least 82 confirmed moons, the second most of any planet. Titan, the largest, is bigger than Mercury and possesses a thick atmosphere, denser than Earth's. This atmosphere, mostly nitrogen with traces of methane, creates a greenhouse effect that warms Titan's surface to about minus 179 degrees Celsius, cold but warm enough for methane to exist as liquid. Rivers and lakes of liquid methane and ethane dot Titan's surface, making it the only place besides Earth with stable liquid on its surface. Titan's atmosphere is so thick and hazy that its surface remained hidden until radar penetrated the clouds. The Huygens probe, released by Cassini in 2005, descended through this atmosphere and landed on Titan's surface, transmitting images of a world that looked strangely familiar: rounded cobbles on a sandy plain, shaped by flowing liquid, though the liquid was methane rather than water, and the temperature was cold enough to freeze air solid. Enceladus, a small moon only 500 kilometers in diameter, displays some of the most exciting geology in the solar system. At its south pole, Massive plumes of water vapor and ice particles erupt from cracks in the surface, shooting hundreds of kilometers into space. These plumes indicate a subsurface ocean, kept liquid by tidal heating from Saturn's gravity. Cassini flew through these plumes, analyzing their composition, finding not just water, but organic molecules and energy sources that could support life. Iapetus, another of Saturn's moons, has a two-toned appearance, one hemisphere bright as snow, the other dark as coal. The bright side reflects 50% of sunlight, while the dark side reflects only 3%, making them among the brightest and darkest surfaces in the solar system. This coloration likely results from dark material, possibly from another moon, coating one hemisphere which then absorbs more heat, causing ice to evaporate and redeposit on the colder, brighter side, amplifying the difference over time. Uranus orbits on its side, its axis tilted 98 degrees from vertical. Where other planets spin like tops, Uranus rolls like a ball, its poles alternately pointing toward and away from the Sun as it orbits. One pole experiences 42 years of continuous sunlight, then 42 years of darkness. What caused this extreme tilt remains debated. Likely a massive collision early in the planet's history knocked it sideways, an impact violent enough to reorient an entire world. This unusual orientation creates extreme seasons. During solstice, one pole points directly at the sun, while the other points into deep space. Yet surprisingly, Uranus's equator is not significantly warmer than its poles, and the planet actually emits very little internal heat compared to other giant planets. Why Uranus generates so little internal energy remains a mystery. Perhaps that ancient collision that tilted it also disrupted its internal heat, or perhaps its composition differs subtly from Jupiter and Saturn in ways that affect heat retention. Uranus appears as a featureless blue-green sphere in most images, its color caused by methane in the atmosphere that absorbs red light. Unlike Jupiter and Saturn with their dramatic bands and storms, Uranus seems calm, though this appearance is partly an artifact of observation. Recent images from more powerful telescopes reveal subtle cloud bands and storms, the planet more dynamic than it first appeared. Winds blow at hundreds of kilometers per hour, even if the atmosphere lacks the dramatic colors of Jupiter. Like other giant planets, Uranus has rings, though far fainter and narrower than Saturn's. These rings are dark, reflecting only about 2% of incident light, making them difficult to detect. They weren't discovered until 1977, when astronomers noticed starlight dimming in a pattern as Uranus passed in front of a star. The rings consist of dark particles, possibly organic compounds darkened by radiation, very different from Saturn's bright ice. Uranus has 27 known moons, named after characters from Shakespeare and Alexander Pope rather than Greek mythology like most solar system bodies. Miranda, the innermost large moon, displays some of the strangest geology in the solar system, with cliffs twice as high as Everest, canyons deeper than the Grand Canyon, and wildly different terrains squeezed onto a small body only 470 kilometers across. It looks like it was smashed apart and reassembled, and perhaps it was, surviving one or more catastrophic collisions. Neptune, the outermost major planet, appears deep blue, a richer color than Uranus despite having similar atmospheric composition. The source of this deeper color isn't fully understood, Both planets contain methane that absorbs red light, but Neptune's blue appears more saturated, possibly due to an unknown component in the atmosphere or differences in atmospheric structure. Neptune orbits 30 times farther from the Sun than Earth, receiving 900 times less sunlight, yet it radiates more than twice as much energy as it receives, internal heat driving powerful atmospheric dynamics. Neptune experiences the fastest winds in the solar system, exceeding 2,000 kilometers per hour. The mechanism driving these winds on a planet so far from the Sun remains somewhat mysterious. The internal heat generated by the planet's slow contraction and radioactive decay must power the atmospheric circulation, but the details of how this creates such extreme wind speeds aren't fully understood. Neptune proves that distance from the Sun doesn't mean calm conditions. When Voyager 2 visited Neptune in 1989, it observed a great dark spot, a storm system similar to Jupiter's Great Red Spot. But when the Hubble Space Telescope observed Neptune several years later, the Great Dark Spot had disappeared and new spots had formed elsewhere. Neptune's storms appear more transient than Jupiter's, forming and dissipating on time scales of years rather than centuries. The planet's weather remains dynamic, clouds and storms constantly appearing and vanishing. Neptune has 14 known moons, the largest being Triton, a world nearly as large as Europa. Triton orbits Neptune backward, opposite to the planet's rotation, suggesting it wasn't formed alongside Neptune but was captured, likely from the Kuiper Belt. This capture would have had dramatic consequences, disrupting any existing moon system, generating intense tidal heating that might have melted Triton's interior, explaining the relatively young surface with few impact craters. Triton is one of the coldest objects in the solar system, with surface temperatures around minus 235 degrees Celsius. Yet, even at this extreme cold, it displays geological activity. Voyager 2 observed geysers erupting from Triton's surface, dark material shooting 8 kilometers high, then drifting downwind in the thin atmosphere. These geysers probably result from nitrogen ice, absorbing faint sunlight, warming slightly below the surface until pressure builds enough to breach the crust, a solar-powered process functioning at temperatures that would freeze air solid. Beyond Neptune lies the Kuiper Belt, a region of icy bodies extending from Neptune's orbit to about 50 astronomical units from the Sun. Like the asteroid belt, but far larger and more massive, the Kuiper Belt contains remnants from the solar system's formation, material too dispersed to coalesce into planets. Pluto, once considered the 9th planet, is actually one of the larger Kuiper Belt objects, reclassified as a dwarf planet when astronomers realized it shares its region with numerous similar bodies. Pluto orbits at an average distance of 39.5 astronomical units from the Sun, taking 248 years to complete one orbit. Its orbit is more elliptical and tilted than the major planets, occasionally bringing it closer to the Sun than Neptune, though the two never collide because of orbital resonances. Pluto rotates slowly, tidally locked to its largest moon, Charon, both bodies keeping the same face toward each other, a double planet system orbiting a common center of mass. New Horizons spacecraft flew past Pluto in 2015, revealing a surprisingly complex and active world. Mountains of water ice, some as tall as the Rockies, rise from the surface. A vast plain of nitrogen ice, informally named Sputnik Planitia, shows signs of recent geological activity. convection cells where nitrogen ice slowly churns. Glaciers of nitrogen ice flow through valleys. Pluto, despite its small size and distance from the Sun, remains geologically alive, driven by internal heat and the cycling of surface ices. Charon, Pluto's largest moon, is unusually large relative to its primary. Pluto and Charon form a binary system more than a planet and moon. Charon's surface differs from Pluto's with water ice rather than nitrogen ice dominating. A dark red region, informally called Mordor Macula, covers Charon's north pole, colored by organic compounds called tholins, created when ultraviolet light and cosmic rays process methane from Pluto's atmosphere that has been captured by Charon. The Kuiper Belt extends beyond Pluto, containing perhaps hundreds of thousands of objects larger than 100 kilometers. Eris, another dwarf planet, is about the same size as Pluto, but more massive. Its discovery in 2005 prompted the debate that led to Pluto's reclassification. Other notable Kuiper Belt objects include Makemake and Haumea, the latter spinning so fast that centrifugal force has stretched it into an elongated ellipsoid, a spinning football of ice and rock. Beyond the Kuiper Belt, at about 100 astronomical units, lies the heliopause, where the solar wind meets the interstellar medium. This boundary marks the edge of the Sun's influence, where outflowing particles from the Sun can no longer push back the thin gas between stars. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. Though it still technically orbits the Sun, still part of the solar system in the gravitational sense. The Oort cloud, a theoretical sphere of icy bodies, is thought to surround the solar system at distances from 2,000 to 100,000 astronomical units. This cloud, never directly observed, contains trillions of comets, pristine remnants from the solar system's formation, gravitationally bound to the Sun but barely, residing in a realm where nearby stars exert almost as much gravitational influence as our Sun. Occasionally, passing stars or galactic tides perturb these distant comets, sending them falling inward toward the Sun on orbits that take millions of years to complete. Comets, those visitors from the outer darkness, display spectacular tails when they approach the Sun. The solid nucleus, typically a few kilometers across, consists of ice and dust. A dirty snowball, as astronomer Fred Whipple described them. As a comet nears the Sun, heat vaporizes surface ice, releasing gas and dust that form a vast coma around the nucleus and stream away from the Sun in tails that can stretch millions of kilometers. Comets actually develop two tails, a dust tail, pushed by the pressure of sunlight, curving slightly along the comet's orbital path, and an ion tail, blown directly away from the Sun by the solar wind. The ion tail, composed of charged particles, glows blue from fluorescence, while the dust tail reflects sunlight and appears yellowish white. These tails always point away from the Sun regardless of the comet's direction of travel. So a comet leaving the solar system travels tail first. Some comets orbit the Sun regularly, like Halley's Comet, which returns every 76 years. Edmund Halley realized in 1705 that comet sightings from 1531, 1607, and 1682 represented the same object and predicted its return in 1758. He didn't live to see his prediction confirmed, but when the comet returned as forecasted, it was named in his honor. Halley's Comet has been recorded throughout history, appearing in Chinese chronicles, Babylonian tablets, the Bayeux Tapestry. Returning reliably through millennia, meteor showers occur when Earth's orbit intersects debris trails left by comets. As cometary ice vaporizes, it releases dust particles that spread along the comet's orbit. When Earth passes through these streams, particles hit the atmosphere at high speed, burning up from friction and creating the streaks of light we call meteors or shooting stars. The Perseid meteor shower in August comes from debris from Comet Swift-Tuttle, while the Leonids in November trace back to Comet Tempel-Tuttle. Most meteors vaporize completely in the atmosphere, but larger pieces can survive to reach the ground as meteorites. These rocks from space, once they're found on Earth's surface, provide samples of asteroids and occasionally other worlds. Some meteorites clearly originated on Mars, blasted into space by asteroid impacts, wandering through space for millions of years before falling to Earth. Others come from the asteroid belt, and some rare ones might even derive from comets, though these are harder to identify. The Sun dominates the solar system, containing 99.86% of the system's total mass. All the planets, moons, asteroids, comets, and dust combined make up less than 0.14%. If the Sun were hollow, it could contain over 1 million Earths. Despite this immense size, the Sun is only a medium-sized star classified as a G-type main sequence star or yellow dwarf. About half of all stars are smaller and cooler, half larger and hotter. The Sun generates energy through nuclear fusion in its core, where temperatures reach 15 million degrees Celsius and pressures are enormous. Under these conditions, hydrogen nuclei overcome their electrical repulsion and fuse together, forming helium and releasing energy. This energy takes thousands of years to work its way from the core to the surface, bouncing between particles in a random walk, before finally escaping as light that reaches Earth in only 8 minutes. The Sun's surface, the photosphere, displays features that reveal the seething activity within. Sunspots, darker regions cooler than their surroundings, mark areas where magnetic fields inhibit convection, preventing hot material from rising. These spots come and go in an 11-year cycle, periods of high activity, with many spots alternating with quiet periods when the Sun's face appears nearly blank. This cycle affects Earth subtly, correlating with small variations in climate, though the Sun's output changes by less than 0.1%. Solar flares and coronal mass ejections hurl energetic particles and magnetic fields into space. When directed at Earth, these events can disrupt satellites, damage power grids, and create beautiful auroras as charged particles interact with our magnetic field and atmosphere. The auroras, northern and southern lights, occur when solar wind particles funnel along magnetic field lines toward the poles, exciting atoms in the upper atmosphere that then emit light. Curtains of green and red dancing across polar skies. The solar wind, a constant stream of charged particles flowing outward from the Sun's corona, reaches Earth at speeds of 300 to 800 kilometers per second. This wind pushes against Earth's magnetic field, compressing it on the sun-facing side and stretching it into a long tail on the night side. Without our magnetic field, the solar wind would gradually strip away Earth's atmosphere, as happened to Mars billions of years ago when its magnetic field shut down. The Sun has been shining for about 4.6 billion years and will continue for another 5 billion. It's currently in the main sequence phase, steadily fusing hydrogen into helium in its core. Eventually, the hydrogen in the core will run out. Unable to generate energy through fusion, the core will contract and heat up, while the outer layers expand, the sun swelling into a red giant. It will grow so large that it might swallow Mercury and Venus, and possibly Earth, though our planet will certainly become uninhabitable long before then. After the red giant phase, the sun will shed its outer layers, creating a planetary nebula, a glowing shell of gas expanding into space, lit from within by the exposed core. That core, no longer generating energy through fusion, will cool and shrink, becoming a white dwarf, an Earth-sized ember composed of carbon and oxygen, slowly radiating its residual heat into space over trillions of years. Eventually, after time periods longer than the current age of the universe, the sun will fade completely, becoming a black dwarf, a cold, dark sphere of degenerate matter. But all of this lies billions of years in the future. For now, the sun shines steadily, providing the light and warmth that makes life on Earth possible. Every photon of sunlight began as energy released by fusion in the solar core thousands of years ago, worked its way to the surface through countless collisions, then raced across space to touch your skin, to warm the ground, to feed the plants that feed us. We are children of the sun, made from material forged in stars, living on energy from fusion, planning futures beneath its light. The solar system, this small corner of space, represents home for everyone who has ever lived. All human history, every civilization, every story, every individual existence has occurred on or near Earth, under the light of this one star. The cosmos extends infinitely beyond, containing hundreds of billions of galaxies, each with hundreds of billions of stars, many certainly with their own planets. Yet this system, these worlds orbiting this star, remain the only ones we've touched, the only ones we truly know. Spacecraft have now visited every planet, have landed on asteroids and comets, have sampled Saturn's rings and tasted the geysers of Enceladus. Rovers explore Mars, searching for signs of ancient life. Probes have plunged into Jupiter's atmosphere and orbited Saturn for years. New Horizons revealed Pluto's heart-shaped plane and then flew past Arrokoth, a contact binary in the Kuiper Belt, the most distant object ever visited. We've begun to know our neighborhood in detail, these worlds becoming places rather than just points of light. Yet for all we've learned, mysteries remain. Does life exist elsewhere in the solar system? Perhaps in Europa's ocean or on Enceladus? Or perhaps did life once flourish on early Mars? How did the giant planets form and migrate? What triggered the late heavy bombardment that scarred the inner planets 4 billion years ago? Why does Venus lack plate tectonics while Earth has them? Why does Uranus generate so little heat? Every answer raises new questions. Each mission reveals new puzzles. Future missions will continue exploration. NASA plans to send a probe to Europa, drilling through ice to sample the subsurface ocean. A spacecraft will visit Titan, deploying a helicopter to explore its atmosphere and surface. Humans may return to the moon, establishing permanent bases, using lunar resources to support deeper exploration. Mars beckons, the most plausible destination for eventual human settlement, though challenges of distance, radiation, and life support remain formidable. Perhaps someday, humans will walk on Europa's ice, will descend through Titan's orange haze, will watch sunrise from Olympus Mons. Perhaps colonies will orbit the sun, harvesting resources from asteroids, building new worlds in space. Or perhaps we'll remain bound to Earth, learning about distant worlds through robotic proxies while cherishing this one precious planet. The future remains unwritten, possibilities stretching before us like the space between stars. For now, we observe from Earth this small world, this blue marble suspended in darkness. We send our machines ahead, our eyes and hands extended across the solar system. We learn, we wonder, we imagine. The cosmos reveals itself gradually, each discovery a gift, each image from distant worlds a reminder of the universe's beauty, complexity, strangeness. We live in a time when the solar system has begun to feel familiar, when Pluto has a face, when Saturn's rings have names, when Mars is a place where robots have spent years exploring. The knowledge we've gained, these 100 facts and countless more, represents humanity's collective achievement. Centuries of observation, calculation, imagination, and exploration. From Galileo's first telescopic observations of Jupiter's moons to New Horizons' flyby of Pluto, from discovering Neptune through mathematical prediction to landing rovers on Mars, each step built on previous ones, each generation seeing farther, understanding more deeply. Yet, knowledge isn't the only gift of exploration. There's also perspective, the profound shift in how we see ourselves that comes from viewing our planet from space, from understanding our place in the cosmic context. We orbit an ordinary star in an ordinary galaxy, one planet among countless billions, yet also something precious. The only place we know for certain harbors life, consciousness, the ability to wonder at existence itself. As you rest tonight, the solar system continues its ancient dance. Mercury races around the sun, Venus rotates slowly backward, Earth spins through day into night, Mars orbits through its long year. Jupiter's great red spot swirls, Saturn's rings catch and scatter sunlight, Uranus rolls along its tilted axis, Neptune's winds howl in darkness, Pluto and Charon circle each other, Kuiper Belt objects slowly tumble through space, and distant comets fall inward from the Oort cloud on their million-year journeys. All of this happens whether we observe it or not, whether we understand it or not. The cosmos operates according to laws we've only begun to decipher, patterns we've barely glimpsed. Gravity, electromagnetism, quantum mechanics, nuclear forces, these shape everything from atoms to galaxies, from the fusion in stellar cores to the orbits of planets, from the chemical bonds that make life possible to the light that lets us see. We are part of this, made of atoms forged in stars that died before the sun formed, made of material recycled through multiple generations of stellar birth and death. The iron in your blood, the calcium in your bones, the carbon in your cells, all created by nuclear fusion in stars, all scattered by supernovae, all gathering into the cloud that became our solar system. You are, quite literally, stardust, the universe organized into a form that can contemplate itself. Let that thought be the last you hold before sleep. You are stardust. You are a way for the cosmos to know itself. You orbit a star on a planet that orbits that star, in a solar system that orbits the galactic center, in a galaxy that's part of a local group, in a universe vast beyond comprehension. And yet, you are here, aware, alive, part of this cosmic story still unfolding. The solar system continues its journey through space, orbiting the galactic center at 230 kilometers per second, taking about 225 million years to complete one galactic orbit. The Sun has completed about 20 orbits since its formation, and will complete perhaps 20 more before it dies. We live in one brief moment of this journey, one small chapter in a story billions of years long. Rest now with the knowledge that you're part of something immense, something beautiful, something still mysterious despite all we've learned. The universe doesn't need to be understood to be wonderful, though understanding adds another layer of appreciation. You can rest in the darkness, part of the cosmos, part of the eternal dance of matter and energy through space and time. The solar system will be here when you wake. The sun will rise, Earth will turn, the moon will follow its orbit. These ancient patterns continue, reliable, steady, indifferent to human concerns, yet providing the stage on which all human concerns play out. We are guests on this world, temporary inhabitants of this moment, yet also integral parts of the whole, participants in existence itself. Let your breathing slow. Let your body settle into rest. Let thoughts of distant worlds, of ancient collisions of ice and fire and stone drift through your mind like comets through space, appearing briefly, then fading into darkness. You don't need to hold on to any of it. The knowledge is there, stored somewhere in the networks of your brain, available when needed, resting when not. Sleep well, traveler. Dream of worlds beyond this one, or dream of nothing at all. Either way, you're part of the cosmos, part of its long, slow evolution from simplicity to complexity, from matter to life to consciousness to wonder. That's miracle enough for one small life, one brief moment between darkness and darkness. The solar system holds many wonders, but none more wonderful than the fact that part of it has become aware, has opened eyes and looked out at the rest, has asked questions and sought answers, has felt awe at the immensity and beauty of it all. That part is you. Rest now. The stars will wait. Good night.